Hello there, Mr. Sutton with this lesson on the geometric, nth term, and ratio tests. In this one, we're going to determine whether a series converges or diverges using these three tests. Before we launch into our warm-up, let's just define a few terms here. We say an infinite series converges if its sum is a single finite number. Both of these pieces are important. We diverge if the sum is either infinite or if it's not a single number, if it oscillates between two or more numbers. And why do we care about this? Well, a series that converges can be used to approximate functions like we did a few lessons ago. A diverging one can't. So all that work we already did is for naught if we don't have a converging series. With that in mind, determine if this series converges or diverges. Justify your answer, and then if this does converge, figure out its sum. Pause the video and see if you can do this. All right, so you might recognize, and this is the key on this one, that this is a geometric series. Our A1 value, our first term is 3, and we have a common ratio of, let's see, -6 divided by 3. That would be -2. So we might remember that there's a formula for the sum of an infinite geometric series. But before we can use that formula, we need to make sure the ratio meets certain conditions. Otherwise, we get just the wrong answer. So what you were doing back in the day when you verified these conditions was actually something called the geometric series test, which says if our common ratio, the absolute value of it, is less than 1, the series will converge. The series is slowing down enough to converge. If the absolute value of r is greater than or equal to 1, then our series is going to diverge off into infinity. So in this case, the absolute value of our common ratio is 2. Since 2 is greater than or equal to 1, that means that this series is going to diverge by the geometric series test, and there's no point in trying to find its sum. Here's another example for you to try out. Figure out convergence, divergence of this series based on what we just went over, and then see if you can find the sum. All right, so for this one, it's hard to see that this is a geometric series unless you do a little rearranging. I mean, you could write out the first few terms of the series and then you would see it. But if we split this 2 up, we can actually make this 2 times 2 to the n. And then if we wanted 2 to the n over 3 to the n, we can make that 2/3 raised to the nth power. And now we see, since we have repeated multiplication here, we definitely have a geometric series. So in these situations, we again like to find the a1 and the r values. For a1, my first term, that's what I get when I plug in 1. That would be 2 times 2 over 3 to the first, so 2 times 2/3, which is 4/3. Common ratio is what I keep multiplying by. That's 2/3. Now we see here, since the absolute value is 2/3, and since that is less than 1, this series is definitely going to converge by our geometric series test. So that means we can actually figure out the sum of this series. Do you remember the formula for that one? So the sum, we actually did this when we were writing series out in the last packet. That's going to be a1 over 1 minus r. So that's just going to be 4/3 over 1 minus 2/3. And then just simplify as much as you can. 1 minus 2/3, that's going to be 1/3. 4/3 over 1/3, that's just going to be 4. Here's another problem for us to look at. We can only find the sum of an infinite geometric series, but other series we can at least still figure out whether it converges or diverges. So for this one, how would we proceed? Well, the first thing to notice about this, and you might have picked up on this is not a geometric series. So we can't use our geometric series test on this one. But that doesn't mean our geometric series test is completely useless. Let's ask the question, why does it make sense that a geometric series will converge if absolute value of r is less than 1? Specifically, what is happening to the nth term? Take a moment to think about this. So if your absolute value of r is less than 1, that means that the things you're adding are getting smaller and smaller and smaller. Specifically, the nth term is going to be approaching 0 if you go on long enough, which means that if you're adding things that are getting infinitely small, your series is essentially slowing down. Now, this means, kind of looking at it from the other perspective, if your nth term is not approaching 0, if the things you're adding are kind of staying put at like 1, you're adding 1 over and over again, or even worse, if the things you're adding are getting bigger and bigger, that means your series is going to have to grow without bound. So this realization here about the nth term being 0 or not leads us to what we call the nth term test. And to talk about what the nth term is approaching, we have to talk about the limit of the nth term. So limit as n approaches infinity of the nth term. If this is anything but 0, if it's infinite, if it's some other finite number, then that means that the series with this nth term is going to have to diverge. Now notice that this test doesn't say anything about the series converging if the limit does approach 0, because that's not going to be enough to prove convergence. Mathematicians often call this test kicking the tires. When you buy a car, the philosophy is you should kick the tires, and if they fall off, you don't buy the car. So you always do this test first just to make sure there's nothing really wrong with the series. But if you kick the tires and they don't fall off, that doesn't mean you've got a good car. It just means you have to do other tests. So we can't prove convergence with this. We can only prove divergence. But it at least saves us time from running other tests. So pause the video and see if you can use the nth term test on this series down here. All right, so to use the nth term test, it's actually pretty straightforward. We just take the limit of the nth term, so limit of n over n plus 1 as n approaches infinity. And we have to be really good at taking infinite limits here. So this is a choose your champion thing. The champion in the top is n because there's no one else. On the bottom, it's also n. N over n just reduces to 1. Now, the important thing here is that this does not equal 0. Since our nth term is not 0, we would say this series diverges by the nth term test, and we don't have to keep testing it. So I personally think the nth term test is a whole lot of fun. Here's some more fun for you. Pause the video and wrestle with these ones. All right, so for this one, I always try the nth term test first, no matter what. So limit of this expression here, we have an exponential term on the top. We have a polynomial on the bottom. Exponential growth is faster than polynomial growth. So this is a top-heavy function that is just going to approach infinity. Now again, we don't really care what it approaches if it does not equal 0. If it doesn't equal 0, this diverges by the nth term test. Let's try this next one. We have 1 over n factorial. Well, factorial growth beats pretty much everything except for n to the n. So this is definitely a bottom-heavy function, which means the limit of this nth term is going to be 0. Now, this means that this series might converge. But again, the nth term test can't prove convergence. It only eliminates the really bad divergers like this one. So this means we're going to need another test. To figure out what's going on with this series, we're going to expand it. So this is going to be 1 over 1 factorial, or just 1, plus 1 over 2 factorial, 1 over 3 factorial, and so on and so forth. Now, this is clearly not geometric. We're not multiplying by a single number to get the next term each time. But what if we take a look at the individual ratios between these terms? Maybe we'll learn something. So my first ratio, just 1 over 2 factorial over 1, is just 1 over 2 factorial, or just 1 over 2. My next ratio, that's 1 over 3 factorial over 1 over 2 factorial. Well, if I do my little same change flip, that's going to be 2 factorial over 3 factorial, which, if I cancel out the first 2 factorials in the denominator, this is just 1/3. My next ratio is going to be, let's see, dividing this by this, that's going to be 3 factorial over 4 factorial, which is 1 over 4, just 1 over 4. And these keep going. The next one's 1/5. But let's look at these ratios. So we definitely don't have a common ratio, so it's not geometric. But these ratios are less than 1, and it looks like they're just going to keep decreasing forever. The important thing about the geometric series test is that you had a ratio that you knew was going to stay less than 1. So if our ratio here dips below 1, and we can prove it keeps decreasing, that's actually just as good as having a common ratio of less than 1. So this intuition here is what leads us to something called the ratio test. Now, to prove that our ratio is going to keep decreasing, we need to talk about the limit as n approaches infinity of basically the nth ratio. So what that looks like, let's say that L, big L, is the limit as n approaches infinity of, and we'll have to do absolute value here, the n plus 1th term over the nth term. If this nth ratio basically is less than 1, that's like having a common ratio of less than 1 with the geometric series. It shows that we have a converging series. If, on the other hand, this limit is greater than 1, Well, that's like having a common ratio bigger than 1. It proves the series is diverging. It shows the ratios are getting bigger and bigger, so we're adding bigger and bigger numbers as we go. Now, the interesting thing is, if your limit is 1, or if this limit oscillates between two different numbers for whatever reason, then this is actually an inconclusive test, and we have to do more tests. It's just too close to call. So with all of that in mind, let's have a little rematch with this series. We already tried the nth term test and got 0 out of that. So let's try the ratio test on this thing. And in general, when you see factorials, ratio test is a good one. So I'm going to say, I'm going to take the limit of the absolute value of, now I need the n plus 1th term over the nth term. So n plus 1th term, that's going to be 1 over n plus 1 factorial. So I've got my limit as n approaches infinity here. And then I'm dividing that by just the nth term. That's just what you see here, 1 over n factorial. So same change flip, just reducing the fraction here. This is really going to be n factorial over n plus 1 factorial. And we just need to simplify this now. Now the key with these factorials is realizing that n plus 1 factorial is really just n plus 1 times n factorial, which means these n factorials here can cancel, leaving us with just 1 over n plus 1, limit as n approaches infinity. What is this limit going to be? Well, this is a constant over something that's not constant, so this is a bottom-heavy function, which goes to 0. The important thing here is that 0 is less than 1. So this tells us that our series is going to converge by the ratio test. Here's another one for you to try out. Give this one a whirl. All right, so let's see here. We'll try our ratio test on this one. So I have the limit as n approaches infinity of absolute value of big fraction now, n plus 1th term, that's 10 to the n plus 1 over n plus 1 to the 10th, divided by just this expression, the nth term. Setting up my fraction now, same change flip. In my numerator, I've got 10 to the n plus 1 times this n to the 10th that flips upstairs. Downstairs, I have the n plus 1 to the 10th, and also this 10 to the n is coming downstairs. Reducing things a little bit, I can do, let's see, 10 to the n plus 1 over 10 to the n. Well, subtracting the exponents, that just leaves me with 10 to the 1st in the numerator. And I also have an n to the 10th up there still, and I have this n plus 1 to the 10th downstairs. Now, as n approaches infinity, this lesser term of 1 can just go away. So we essentially have n to the 10th downstairs. Reducing here, this is just going to be 10. Significantly, since this is greater than 1, we can conclusively show this series diverges by the ratio test. Awesome. But hold on a sec. Did you ever stop to kick the tires on this one? What's the limit of my nth term? Well, this is a top-heavy function. Exponential growth beats polynomial growth. So this actually goes to infinity. Since infinity is not 0, we could also have shown, much faster actually, that this thing diverges by the nth term test. And in general, it turns out anything that diverges by the geometric or ratio test also diverges by the nth term test. So always kick the tires first. We'll finish this one out with one more example. This is called the Harmonic Series now. This is a special series, sum of 1 over n from 1 to infinity. So this is 1 plus 1 over 2 plus 1 over 3 and so on and so forth. Pause the video and run some tests on this one. All right, so hopefully you started with kicking the tires with our nth term test. Limit as n approaches infinity of 1 over n. Well, this is just going to 0, so that doesn't tell us a whole lot. Next, we try the ratio test. I mean, it's not geometric, so we can eliminate that one right away. But our ratio test, we have the nth term, 1 over n plus 1, divided by the nth term, 1 over n. And this is really just going to be n over n plus 1 as n approaches infinity, which goes to 1, which also doesn't tell us a whole lot. So it turns out we don't know enough to deal with the harmonic series yet, but we will. Stay tuned for the next lesson. Until next time, Mr. Sutton signing off.